Welcome to day 92. We tend to think of modern AI models as being incredibly reliable, and they are, most of the time. But what if that reliability is actually more fragile than it seems? So let's take a look. Here we have a pretty standard state-of-the-art AI model. You show it this picture, and it tells you with 99% confidence that's a panda. And you know what? It's right. This is exactly what we expect from these systems. But here's where things get interesting. What if we could change this image just a tiny bit, in a way you and I would never even notice, but in a way that could make the machine see something completely different? And here you go. We're looking at the same model and what looks like the exact same image. But it's not. A very specific, mathematically designed layer of noise has been added. And now, the model isn't just wrong, it's confidently wrong. It's now 93% sure that this is a given. This right here is an adversarial attack. By the end of this explainer, you're going to understand exactly how this kind of deception works, why it's not just a random fluke, and why it's one of the biggest security challenges we face in machine learning today. All right, let's start with a clear definition. What exactly is an adversarial attack? In short, it's a way to intentionally trick a model. An attacker creates some sort of deceptive data, feeds it to the model, and the whole point is to make the model fail, either by giving a wrong answer or just behaving in a way it was never supposed to. Now, to get a real feel for this, let's set the tech aside for a second and use an analogy. It helps explain why these attacks work on machines, even when they're totally invisible to us. So I want you to imagine our AI model is like a castle guard. This guard is an absolute expert, trained on thousands of scenarios to spot an enemy. But the guard has a weakness. It follows its rulebook to the letter, with zero room for common sense. It's great at seeing patterns, but it doesn't understand purpose. Now, along comes an attacker. Let's say it's a banished prince. He knows he can't just break down the gates. The defenses are too strong. So instead, he studies the guard's rulebook. He finds a loophole, and he creates the perfect disguise. Maybe it's just wearing a specific feather in his cap that the rulebook says only friends of the king wear. Now, to any normal person, he's still obviously the banished prince. But to our very literal-minded guard, that one tiny detail, that feather, is all that matters. The rule is exploited, and the prince walks right in. That's exactly how adversarial attacks work. They don't break the model. They just exploit its own logic. And that brings us to a really crucial point, which this quote sums up perfectly. The stuff added to that panda image wasn't just random static. It was a carefully crafted, deliberate pattern designed for one purpose, to fool that specific model's way of thinking. Okay, now that we have the intuition, let's zoom in a bit on the mechanics. How do these attacks actually work in practice? Well, we usually put them into two main buckets based on what the attacker knows. A white box attack is when the attacker has the blueprints to the castle. They know everything about the model's architecture. But in a black box attack, they're working from the outside, just sending things in and watching what comes out to figure out a weakness. We also categorize them by when they happen. A poisoning attack happens while the model is still learning. Think of it like someone sneaking mislabeled photos into the guard's training manual. An attacker might subtly add thousands of images of stop signs labeled as speed limit to a giant dataset. The more common type, though, is an evasion attack. That's our panda example. This happens after the model is fully trained and out in the world, and the goal is just to fool it with one cleverly designed input. So a real-world attack isn't random, it's a process. First, an attacker studies the system to find a weak spot. Second, they craft that special input, the disguise. Third, they deploy it. And finally, they get what they wanted, whether that's just a misclassification or a complete system bypass. And I want to be clear, this isn't just some academic thought experiment. These vulnerabilities have very real and sometimes very serious consequences. You can see this threat popping up everywhere. It could be a self-driving car misreading a road sign, a medical AI misdiagnosing a tumor. Or it could be something we see every day, like spam filters being tricked, or facial recognition systems being fooled. We even saw it with Microsoft's Tay chatbot, where users poisoned its learning process and turned it toxic. And these attacks can even jump into the physical world. This is a wild one. Researchers 3D printed this turtle, but they gave it a specific computer-generated texture. To you and me, it's just a turtle. But to Google's Vision AI, that texture was such a strong signal that it classified the turtle as a rifle with high confidence. And here's an example that really brings it home if you're building real-world systems. Researchers found that by putting just a few small pieces of tape on a stop sign, they could make a self-driving car's AI classify it as a speed limit 45 sign. It just shows how a simple physical trick can defeat an incredibly complex digital system. So if you remember just one thing today, make it this. A model's greatest strength, its amazing ability to find subtle patterns in data, is also its greatest weakness. Adversarial attacks simply turn that intelligence against it. And that leaves us with a pretty big question. As we build more and more systems that make decisions on their own, how do we actually defend against an attack that we as humans can't even see?